When I take a sample from a population and I find the mean of that sample, I want to be able to say something about the population mean in relation to that sample mean. Now, when my sample size is large, it actually turns out that my sample mean is likely a very accurate estimate of the population mean. So that'll give me a point estimate of the population mean. Now, if I want an interval estimate, I can rely on the idea that my sample size is large. Remember, if n is greater than or equal to 30, 30 was that magic number for us for our sample size, to be able to apply the central limit theorem and say that our probability distribution of our sample is approximately normal. And we can make use of that approximate normal distribution to find an interval estimate. So when we talk about finding a confidence interval and we have an approximately normal distribution, now I've drawn what our approximately normal distribution might look like. And if we want a 1 minus alpha confidence interval, we want to find the values that are equal distances from the mean, that when we look at the area under the curve that represents the distribution between those two values, the area is 1 minus alpha. Now, this is equivalent to saying I want to find the z value where the area to the left of it is alpha divided by 2. I'm going to denote that as negative z sub alpha divided by 2. And to find the z value, that'll be the positive version of that, where the area to the right will be alpha divided by 2. So if I put the two areas that are not included together, I'll have alpha plus 2 times 2, or just alpha. And that'll be the part that I'm subtracting from 1. So what I'm really finding is that I want the probability that z is between negative z sub alpha divided by 2 and z sub alpha divided by 2 is equal to 1 minus alpha. Now, the central limit theorem says that I'm going to calculate z by taking the mean of the sample, that point value, subtracting from it the mean of the population, and dividing by the standard deviation of the population divided by the square root of the sample size. So if I want to find a confidence interval on the mean of the population, and I know the variance of the population, then solving for the mean of the population right here gives me this inequality here, where I'm going to be looking for my sample point mean, subtracting from that the z value that gives me an area of alpha divided by 2 to the right, multiplying by the standard deviation of the population divided by the square root of the sample size. And on one side of the mean, on the lower side, I'll be subtracting. On the upper side, I'll be adding. And that's going to give me my 1 minus alpha % confidence interval. So this looks like a lot of variables being thrown around, but what's going to happen is you're going to be able to find your z sub alpha divided by 2 using the table that we used for the normal distribution. The sample size is going to be given to you, so you'll know n. The variance is known and will be given to you, so you'll just be taking the square root of the given variance to find the standard deviations here. And then all that's left is the mean of the sample that you're working with, right there. And that's all there is to it. So it's really one, maybe two things you need to find. Everything else you'll be given directly. So just don't get too worried about there being so many variables floating around. So we have two theorems, and more or less what these are doing is giving you kind of a little bit more of an interpretation of the confidence interval. So the first one says if x bar is used as an estimate of mu, so my sample mean is used as an estimate of my population mean, we can be, whatever confidence interval we're working with, confident that the error will not exceed, and what we're looking at here is the difference between the upper end of our confidence interval and our mean. So it won't exceed z sub alpha divided by 2 times the standard deviation of the population divided by the square root of the sample size. Now, there's another theorem that is basically a direct result of that. It's the same idea. We're going to use the sample mean. It's used as an estimate of the population mean. And we can be whatever % confident that the error will not exceed a specified amount E when the sample size is. Now, the way that this is found is E is set equal to this part from theorem 1 that I know the error won't exceed. So z sub alpha divided by 2 times sigma divided by the square root of n. So all I'm doing is going to solve for my sample size right here, and I'm going to have the result of this theorem. So doing that, I'll have E divided by z sub alpha divided by 2 divided by the standard deviation is going to equal 1 over the square root of n. And then I need to find the reciprocal of both of these sides. So this is going to really say that z sub alpha divided by 2 times the standard deviation divided by E is going to equal the square root of n. And squaring both sides, I get the result of my theorem that says that n equals z sub alpha divided by 2 times the standard deviation divided by E, the quantity squared. So that is my second theorem. Now, notice that we just used the first theorem to get to the second theorem. So really, as long as you can do this algebra, then you don't need to know both of these theorems. You can know the first one and know what you need to do to get to the second one. Now, everything we've talked about has been two-sided confidence intervals where we're going to have a lower bound and an upper bound. Now, there are many times, especially in engineering, where we really only care about one-sided confidence intervals. We want to be sure that something's not going to break, but if it's a little bit stronger than we need it to be, then it's not a big deal. So when we need just one-sided confidence bounds, then instead of using alpha divided by 2, we use alpha for our z's. And if we're taking the upper one-sided bound, if we're trying to find it, then we're going to be adding our margin of error to our mean. And if we're looking for that lower one-sided bound, so something that we're guaranteed that everything falls above, we're going to be taking our mean and subtracting that margin of error that we have. Otherwise, everything about one-sided confidence bounds is pretty much the same as the two-sided version. When we don't know the standard deviation of the population, then we can use the t statistic to help us rather than the z statistic. So the t value we already have seen is t equals the mean of the sample minus the mean of the population divided by the standard deviation of the sample divided by the square root of the sample size. Now, just like we could for the z value, we can say that the probability that the t value is between negative t sub alpha divided by 2 and t sub alpha divided by 2 is equal to 1 minus alpha. And that's going to give us this 1 minus alpha confidence interval idea. So again, just like we did for z, with t, you can plug in what t equals. So the t equals thing that you've already remembered, hopefully. You can plug it in for t, and then we can go about solving for the population mean. As we do that, then we progress through and we get to the point where we have this idea that the probability that the sample mean minus this t sub alpha divided by 2 value times the sample standard deviation divided by the square root of the size of the sample is less than the population mean is less than, and then the sample mean plus that t sub alpha divided by 2 value times the sample standard deviation divided by the square root of the sample size. And this probability, we want it to be 1 minus alpha. And this gives us this idea of this 1 minus alpha confidence interval. So I know this population mean is between those two values. So to formalize that, we have this confidence interval on the population mean when our population variance or our population standard deviation, depending on which way you want to think about it, is unknown, because if we know one, we know the other, right? So if we have our sample mean and our sample standard deviation for a random sample from a normal population with unknown variance, then we can take a 100 times 1 minus alpha % confidence interval for the population mean by just doing exactly what we showed we could above, where we have t sub alpha divided by 2 is the t value with the sample size minus 1 degrees of freedom, leaving an area of alpha divided by 2 to the right. Remember, that's the way our t distribution table is set up, that we're looking at area to the right, or probability to the right. So again, all we're going to do is look for the alpha divided by 2 column in our t table, and we're going to look for the n minus 1 row, and that's going to give us the t value that we're going to plug in order to be able to find this confidence interval. We've also been talking about times when the population variance is known. However, there are going to be times when the population variance is unknown. So if our sample size is greater than or equal to 30, and we're using the central limit theorem to say it's approximately normal, we also can use our sample standard deviation to approximate our population standard deviation. So when we do that, then we can have a confidence interval that is our sample mean plus or minus our z value with alpha divided by 2% of the population to the left of it or right of it. And then we multiply times the sample standard deviation divided by the square root of the sample size, rather than the population standard deviation, since we don't know what the population standard deviation is. And again, this is an approximation that is appropriate whenever we have a sample size greater than or equal to 30, and we don't know the population standard deviation or variance to be able to find the standard deviation. Now we've talked about confidence intervals and point estimates. When we were talking about confidence intervals, we were talking about taking a set of sample data and, given that set of sample data, providing a range of values that would cover the value of the parameter. That is, the parameter value, the actual value, would fall within this range with a certain confidence level. Now, when we were looking at single point estimates, with these, we were taking the sample data that we collected, and using that data, we were providing a single value estimate of what a parameter value would be. Now, there's times that we want to use each of these. We need to be able to give a little bit more information about the point estimate, though. We need to be able to talk about the standard error. So point estimates are not always going to be 100% accurate, as you might be able to guess. So we need to be able to say, well, what's the error involved here? Like, if we're off, are we off by a little bit or are we off by a lot? So to find the standard error, what we do is we take the square root of the variance. Now you might remember that we find the variance by taking the variance of the population and dividing by the sample size. So to find the standard error, we take the square root of the variance and find the standard deviation or standard error. And so taking that, we end up with taking the standard deviation or standard error of the population and dividing by the square root of the sample size. So the larger our sample size, the smaller our standard error will be. And the smaller the sample size, the larger the standard error will be. And this makes sense because as the population or as the sample size grows, it approaches the size of the population. And so the likelihood that we're off from the population parameter with our point estimate decreases. So that's really all we have to say about standard error with a point estimate.